Let's talk about diagnostics with VVT. Our first and always rule with anything we can is use as much scan data as possible. There is variable valve timing scan data available along with codes and other things. For instance, here's examples of codes. P0010, intake cam position actuator circuit problem, bank 1. Exhaust cam position actuator circuit problem, bank 2. Intake cam position actuator circuit problem, bank 2, and right down the line. Let's talk about what we do about that. An actuator circuit problem. What that really means is the PCM's determined that the voltage signals do not match the expected values. The control voltage is determined, of course, by the type of control used. High side switching like GM supplies B+ to the control circuit, while low side switching like Ford and most other manufacturers supplies ground. Determine the type of control used, then the duty cycle should dither around 50. A sticking phasor will result in a duty cycle that hangs outside 50 too long. Once you watch a few, you'll understand it. Use the description, the operation of the service manual publications. Like we said, it's an actuator problem. It's a circuit problem. Be vehicle-specific information and get the real schematic. Once you get the schematic like this, you look at it and say, oh, here's where I'm going to start. I can see that the PCM is supplying ground to control the VVT solenoid. Do you have B+? Look at that first rule. We can always have a blown fuse or something that goofs this up. Now, the resistance of this particular one on a Ford is 4 to 6 ohms, which means the max amps when we go to duty cycling is going to be between 2 and 4 amps. First and foremost, check for B+. If you don't have B+, it's not going to work. Like all appliances, we stress this repeatedly. No device can work without proper B+ and a ground. The rules are simple. Do I have B+? Do I have ground? Does the device function as expected? Any device can be tested that way. So we have B+ on one side, we have ground on the other. Can we have current flow? We look and say we got under 700 volts. That means the ground is closed. We look at it with an ammeter. We can take an ammeter in here and use that to make measurements. Now the battery voltage will vary between 12.8 and 13.8. The voltage divided by resistance equals current. And because the applying voltage and resistance varies, you can do your own specifications. For instance, if we have 13.4 volts divided by 4 ohms, we got 3.35 amps. You can calculate that yourself. You can control this solenoid with some scan tools in interactive data. We can use low amps probes to look at the current flow inductively to this while we're doing it. Here's an example from GM using B+ or high side switching. Here we have voltage applied on the brown wire going over to the variable valve control and ground returning back to the PCM. Very simple circuit. Ground is not switching. B+ is switched in this case. High side ground. In this particular case, this GM has 8 to 12 ohms, which means we'll have 1 to 1.5 amps maximum. Now, I hope you've seen what we've done here. We've gotten vehicle-specific data, and we didn't say that current's going to be between 1 and 4 amps. It's going to be 1 to 1.5 on GM, 2 to 4 on a Ford. So pay attention and get the correct data for the vehicle you're working on. As we said before, we're going to come and do the same measurement. Now we're looking for B+. We're going to see if it varies. 0, B+ is open. Look at the bottom, we have very low voltage. The resistance of the control can vary by manufacturer, so pay attention. Determine the maximum current flow by doing a current draw test and doing your own calculation to see if it's right. If the current flow, if maximum current can be reached, the actuator resistance is normal. Check for voltage during normal operation. Something else is wrong if you get this code. Now we're going to talk about the voltage levels measured by a voltmeter on the control circuit. The duty cycle causes the average voltage to vary on the control circuit. And remember, this one is supplying ground. The higher the duty cycle, the closer it is to ground. The lower the duty cycle, the further away it is to ground. That's the opposite of what high side will be when we get to a GM. Here, let's start in the middle. We get 13.8 volts from scan data. We look at our scan tool and it says 50% duty cycle. These two values we're going to look at with ground side switching. If we multiply 0.5 times 13.8, we get 6.9 volts. If we reduce the duty cycle to 40%, that means 40% of the time it's grounded. 60% of the time it's ungrounded. That raises voltage because we have a lower duty cycle. We now have 8.28 volts. But if we increase duty cycle above 50, we now are grounded 60% of the time and ungrounded 40% of the time. Since we're ungrounded only 40% of the time, we multiply 40% times 13.8 and wind up with 5.52. This is the opposite of what happened on high side grounding. Start at the same spot on high side grounding, but when we go to 40%, we have only 40% high side. That gives us 552. Voltage went down because we're looking at the high side. At 60% duty cycle, high side grounding, we're high 6% of the time. That's 8.28 volts. High side is the percentage of time the voltage is high. Low side is the percentage of time voltage is low. Don't let that confuse you. But utilize scan data in this to verify circuit problems. Remember, we came here because the computer has identified a circuit actuator problem. The duty cycle caused the average voltage to vary, and we saw that with a voltmeter. We use an enhanced scan tool that shows the duty cycle for valve timing. Yes, if you got a generic, you will not see duty cycle on variable valve actuator. In fact, a lot of scan tools on earlier cars that had duty cycle on VVT did not show that particular parameter ID. That's a problem we've had. Now here's some data from GM. Cam high to low. This is a simple count. This displays a count of the number of camshaft positions and signal changes as voltage goes from high to low or low to high, whichever way it goes. It's a total count. Is it going up and down the same amount of counts? Cam phase angle, actual degrees. The PCM's commanded camshaft retard in degrees. In this particular case, this vehicle uses cam retard. Indicates fan case desired. This is what the PCM is desired crankshaft angle. Cam duty cycle. This is the one we're just looking at. 0 to 100%. Displays the duty cycle the PCM is applying to the solenoid. Cam phase variation indicates the difference between the desired and the actual camshaft angle. This is important. This is where we see sticking actuators. When we find the PID, it's not always available. Cam reference missed displays the number of cam and crank cylinders missed. 0 is normal, 1 to 8 is not normal. This is particularly beneficial for intermittent conditions. If the signal is missing for a long time, it will read 0. So look at this only for intermittent. Don't look at it as a died in the rule perfect, because a missing, totally gone cam will read 0. But one that's intermittent will have a count. So keep that in mind. It's for intermittent only. Cam retard displays the difference between the camshaft position sensor and the crankshaft position sensor in degrees. We can measure that and read it out. Camshaft signal present displays the number of camshaft position sensor signal inputs to the PCM. Resets to 0 after reading 255. It just counts up, goes down, counts up, goes down, but it shows activity. Indicates the duty cycle command to the different solenoids for bank 1, bank 2. It's a duty cycle where we have V8s or V6s. This indicates, a forward indicates the time the solenoid, warm engine is near 0, warm engine with steady cruise gets near 50%, goes 0 to 99. Error in degrees, 1 is for bank 1, 2 is for bank 2. They don't give us a range, it just indicates the variable. This indicates we have a sticking. When this number goes up and stays there, it indicates a sticking or defective actuator for the cam timing. Cam sync start, yes, indicates the camshaft is locked. No at all of the time. This is on Chrysler. Remember, we have a camshaft that can lock and unlock and change relationship to each other. It's a single overhead cam with variable valve camming. The cam timing position in degrees displays the variations from the learned camshaft position. What did it learn and where is it now? Crankshaft reference in degrees indicates the amount of change in phase between cam and crank signals from the initial set. This indicates the belt stretch or whatever. DC will set at 17% or less, which is about 1 tooth on the belt. So this is telling you something very important for you. This one in Chrysler, we wish we had this everywhere, shows us the amount of belt stretch we have. When you get to 17 or start approaching 17, you need to take action. Compare the average amperage. We're going to be able to use amperage to the duty cycle with amperage. For instance, GM's 50% should have a duty cycle of 0.5 to 0.75. You have to go find the specification. Remember, our specification was 1 to 1.5. Well, 50% is half of that. The voltage should be 6 to 7 volts. They should vary with the duty cycle, as we've talked before. If they don't match, do some circuit testing. Look at the resistance of the solenoid. See if you've got an intermittent connector or wiring problem. Voltage levels on the control circuit is important. The scan data can be used with bidirectional control if it's available to observe the voltmeter and duty cycle relationship if it's not normal. The same data will often have different names with the different scan tools, so be careful. There is no way we can get to everything. Use the support functions of book for the particular scan tool that you're using. You must understand what the PID data is trying to display on your scan tool. We can give you the name, given it to by the manufacturer. Sometimes the abbreviations, they don't come out the same on the scan tool. Sometimes it's a little bit of a learning thing. Excessive current flow indicates a short circuit or a problem with circuit integrity, short to ground or something. Low current indicates high resistance. Check the circuit and actuator for unexpected resistance. That can be in the coil, it can be in connectors, could be in wiring. Usually it's in the coil. If bidirectional scan tool control is available, use it. Turn it on, turn it off. Look at current flow. See if you can reach the minimum to max. If you can't use bidirectional, use jumper leads to take the timing from full retard to full advance to observe the changes in engine speed for phasor diagnostics and measure the amperage for actuator diagnostics. We can use a jumper lead to control the phasor by looking at a manufacturer-specific thing. Here we're looking at a ground actuated. If we supply ground where the arrow is pointing, we will call this to go to full advance. That should cause a change in engine speed, indicating we have advanced or retarded, whichever the case may be. We happen to know in this particular case it would be advanced. Disconnect the actuator, we'll go to full retard. We should expect to see the same thing. Mid-range power will be very low in this case. If opening the circuit gives us full retard, then grounding the circuit must give us full advance. To do this decision making, you must know how your system is wired and what you're controlling. High side circuits need B+ applied to fully advance the intake valve timing. It would be the opposite. We'd have to apply 13.8 to pull it to full vacuum. Now, service codes for the intake side. They indicate the phasor is in the wrong position for the duty cycle commanded. Let's talk about this and see what they say. We're going to be looking at position. The key word to watch for in code definitions is position. P0, 11, intake cam position is over advanced for bank 1, bank 2. Intake cam position is over retarded, bank 1, bank 2, whichever one, 12 or 22. These are all positions. These are the kind of codes we see and problems we have when we have dirt and sludge causing sticky position actuators that don't change position as they should. The advanced code will set when it is requested a retard and the position doesn't change. Remember, this all comes from the relationship of the crankshaft position signal and the camshaft position signal. Don't overlook where the sources come from. Now, the root causes of the failures, oil pressure should be normal at 1500 RPMs for proper vapor operation. On really worn engines, where oil pressure is extremely low, it will not work properly. Oil pressure has to be up in the normal range by the time you get to 1500 because that's where cam timing is going to kick in. Dirty oil, or oil that is the wrong specification, can cause erratic operation. We beat up on that and showed it to you. Whatever you do, check for sludge in the valve cover before you go too far. It can cause any one of these problems. Remember, the dirt and sludge is the root cause of the problem. Don't change any components until you've flushed the engine or made some other arrangements, because putting a new actuator or a new phaser in a dirty engine is only going to go bad again quickly. You must correct the dirty oil problem before you go any further.